Uranus spins completely on its side, a pale blue oddball in our cosmic neighborhood. This often overlooked ice giant is hiding a trove of secrets that defy our basic understanding of planets. By the end of this journey, you will discover 25 of its most baffling mysteries, from a missing heat source to moons that look like shattered puzzles. How did it end up tilted so dramatically, and what creates its wildly off-center magnetic field? What do you think is the most surprising thing a planet can hide this bizarre sideways spin? Is our first great mystery, the extreme axial tilt. While Earth leans at a gentle 23.5 degrees, Uranus is tipped over at a jaw-dropping 98 degrees. It essentially rolls around the Sun like a cosmic bowling ball. This radical orientation completely warps the planet's idea of a year. Imagine a season that does not last for a few months, but for an entire human lifetime. Each pole of Uranus gets 42 years of relentless, unblinking sunlight, followed by 42 years of complete, frozen darkness. The concept of a simple day and night cycle is thrown out the window. So what cosmic event could have knocked a planet so completely on its side? The most compelling theory points to a violent, ancient catastrophe. Astronomers suspect that in the chaotic early days of our solar system, a young Uranus was struck by a protoplanet, a fledgling world perhaps even the size of Earth itself. This titanic collision could have delivered the staggering blow needed to reorient the entire planet. Yet, this explanation is far from settled. If such a colossal impact occurred, where is the evidence? Why does the planet's system of moons and rings also orbit in that same tilted plane, as if the entire system was knocked over in one go? The debate continues to rage, making this not just a question of a planet's position, but a fundamental puzzle about the violence of our solar system's birth. This radical tilt is not the only feature that sets Uranus apart from its planetary neighbors. Its collection of rings presents a second profound mystery, one of shadow and subtle structure. Unlike the brilliant, icy bands that define Saturn, the rings of Uranus are dark and narrow, almost like ghostly circles drawn in charcoal. They were discovered entirely by accident in 1977, when astronomers watched as Uranus passed in front of a distant star. Instead of the star's light simply vanishing, it flickered several times both before and after the main event, revealing the presence of these faint, unseen rings. They are composed not of fine, reflective ice, but of much larger, boulder-sized chunks of material, some as dark as coal. This composition absorbs light rather than reflecting it, making them incredibly difficult to see. But their faintness is only half the puzzle. These rings are also strangely lopsided. They are not perfectly circular, and their density varies in ways that defy simple explanation. Some are confined by tiny shepherd moons, whose gravity acts like a cosmic fence, herding the ring particles and preventing them from drifting away. Yet this only deepens the mystery. Why are these rings so dark and sparse compared to Saturn's glorious system? What ancient event supplied this dusty, boulder-filled debris, and what delicate balance of forces keeps these faint, asymmetrical bands from simply dissolving into space? These faint rings are not the only feature of Uranus that seems fundamentally off balance. Deep within its icy interior lies a force field that defies all convention, a bizarre and chaotic magnetic field. While Earth's magnetic field behaves like a relatively stable bar magnet roughly aligned with our planet's spin, the field around Uranus is tilted about 60 degrees from its rotational axis. It is as if the planet's internal compass is pointing in a completely different direction from the way the world actually turns, but the strangeness does not stop there. This magnetic field is not even centered on the planet's core. It is significantly offset, emerging from a region much closer to the surface. This creates a lopsided magnetic bubble, a magnetosphere that is wildly asymmetrical. As Uranus completes its sideways roll around the Sun, This off-center and tilted field gets dragged through space, creating a magnetic tail that tumbles and twists like a chaotic corkscrew. This bizarre behavior forces us to completely rethink what is happening inside the ice giant. Planetary magnetic fields are typically generated by the churning motion of conductive material deep within a planet's core, a process known as a dynamo. But the standard model of a dynamo cannot easily explain the Uranian field's extreme tilt and offset. This suggests that the dynamo itself is not operating from a deep, stable core of molten metal, but from a strange, layered ocean. Scientists now believe the magnetic field is generated within a superheated, electrically conductive ocean of water and ammonia, a vast mantle of fluid ice under immense pressure. This sloshing, briny sea, churning closer to the surface, could be the source of this unpredictable magnetism. How does such a shallow, fluid dynamo even function? And what does its chaotic nature tell us about the hidden forces at work deep within this enigmatic world? This chaotic magnetic field hints at an even deeper enigma buried within the planet's core, a profound lack of something vital. Uranus is shockingly cold, not just on its cloud tops, but from within. Every planet in our solar system, from tiny Mercury to the gas giants, radiates a certain amount of internal heat left over from its violent formation. This heat flows outward, warming the upper atmosphere and driving global weather systems. Neptune, Uranus's near twin in size and composition, follows this rule perfectly. It glows with internal warmth, radiating about 2.6 times more heat than it receives from the distant sun. This excess energy fuels its supersonic winds and dynamic storms. Uranus, by stark contrast, is a thermal dwarf. It emits barely any internal heat at all. Its energy budget is almost in perfect balance, receiving just about as much warmth from the sun as it gives back. This makes it the only ice giant, and indeed the only major planet without a significant internal heat source. Why is this sibling so frigidly different? The most dramatic theory suggests a cataclysm. That same ancient impact thought to have knocked the planet on its side may have been so violent that it literally scrambled Uranus's interior. The collision could have blasted away much of the planet's original hot core material, leaving behind a stunted, cooled-down remnant. Alternatively, the impact might have churned the interior so thoroughly that the heat was distributed and lost to space in one great thermal pulse, leaving the planet thermally dead. A less violent but equally puzzling idea involves a layered interior. Deep inside Uranus, different layers of slushy ice, rock, and superheated water might be stacked so perfectly that they prevent heat from convecting upwards. Imagine a thermos bottle in space with internal barriers so effective that the core's warmth simply cannot escape. This could leave the planet in a state of profound thermal slumber. Yet neither theory is entirely satisfactory. If an impact stripped its heat, why does Uranus still have a strong magnetic field, which typically requires a warm, fluid interior? And if it is layered like a thermos, what stopped the heat from convecting out billions of years ago? This thermal mystery forces us to question everything we think we know about how planets live, cool, and die. This profound lack of internal heat points directly toward the strange materials that make up the planet itself, leading us to the deep enigma of its icy mantle. When we call Uranus an ice giant, the word ice is deeply misleading. We are not talking about frozen water like you would find in your freezer. The mantle of Uranus is a colossal ocean of superheated, superpressurized fluids, a sloshing sea that might be thousands of miles deep. This is a realm where common substances like water, ammonia, and methane are broken down and reassembled by immense pressure, existing in a bizarre, exotic state of matter that scientists call hot ice or supersonic water. In this strange form, the oxygen atoms from water molecules lock themselves into a rigid crystalline lattice, almost like a solid, while the hydrogen ions flow freely through it like a liquid metal. This creates a substance that is both solid and liquid at the same time, a material that can conduct electricity and generate magnetic fields while behaving unlike anything we can create on Earth. Modeling this exotic ocean is one of the greatest challenges in planetary science. How do you predict the behavior of a fluid that operates under pressures millions of times greater than our atmosphere and temperatures reaching thousands of degrees? This unique composition solves one puzzle while creating another. It perfectly explains the planet's overall density, which is lower than that of Neptune despite their similar sizes, suggesting a greater proportion of these lighter icy materials over heavier rocky elements. It also provides the most likely source for that lopsided, chaotic magnetic field, generated by the churning motions within this electrically conductive, sloshing sea. Yet the fundamental question remains, what is the exact recipe for this vast internal ocean? What precise mix of water, ammonia, methane ices, and other compounds create such a peculiar and powerful dynamo? And how does this hidden chemistry shape the very soul of this distant, tilted world? The very nature of Uranus challenges the story we tell about our solar system's creation. Where and how did this tilted, thermally dead world come to be? Its existence forces us to reconsider the entire process of planetary formation. Standard models suggest that the planets we see today coalesced from a swirling disk of gas and dust around the young sun, with each world forming roughly in its current orbital position. But Uranus and Neptune, the two ice giants, are cosmic outliers. They are too massive to have formed so slowly at their vast distances from the Sun, where material was sparse. This has led to a compelling alternative theory, the idea of planetary migration. Perhaps Uranus was born much closer to the Sun, in a region richer with the icy building blocks that define its composition. Over millions of years, gravitational interactions with Jupiter and Saturn could have flung it outward like a cosmic slingshot to its present cold and distant orbit. This grand tack model would explain its size and makeup, but it raises new and difficult questions. If Uranus migrated, why did it not collect a much thicker atmosphere of hydrogen and helium like Jupiter did? Why does its chemical fingerprint seem so distinct from its sibling Neptune if they supposedly followed similar paths? Its very composition is a fossil record of a different time. The high amounts of methane, water, and ammonia that make up its bulk point toward a formation location that was cold enough for these volatile ices to condense into solid particles, a region known as the frost line. But the precise recipe of its interior, with a seemingly higher proportion of rock and ice compared to gas, does not match any single location in our standard model of the protoplanetary disk. It is as if Uranus was assembled from a pile of cosmic leftovers that should not have existed in one place, a puzzle piece that does not fit the picture we have of the early solar system. Was it truly a wanderer, or did it form in a unique, previously unknown pocket of the disk, a place where the rules of planetary construction were written differently? The origin of Uranus remains one of the most profound open questions, a mystery that forces us to rewrite the very first chapter of our local cosmic history. This quiet exterior, however, is a masterful illusion. For decades, ground-based telescopes showed only a featureless, pale blue-green sphere, a cube ball in the void. This apparent blandness earned Uranus a reputation as the most boring planet in the solar system, a quiet giant seemingly devoid of the raging storms that mark its siblings. The truth, revealed by closer inspection, is a world of subtle, complex, and deeply puzzling weather. When Voyager 2 flew past in 1986, its cameras saw a world in the depths of its long polar winter. The sun was shining directly over the South Pole, leaving the Northern Hemisphere in a 42-year-long night. Even then, scientists expected to see some dramatic atmospheric activity. Instead, they found a world cloaked in a high-altitude photochemical haze, a smog that smoothed over any visible cloud features, presenting that famously blank face to the universe. Only by using advanced image processing and observing in specific wavelengths of light could Voyager detect a handful of faint clouds and a single major storm, a feature nicknamed the Bright Complex. This was a world that seemed determined to keep its secrets. The mystery only deepened with time. Decades later, the Hubble Space Telescope and powerful ground-based observatories equipped with adaptive optics began to pierce the haze. They revealed a world that had awoken. As sunlight slowly migrated to cross the equator, Uranus developed more pronounced cloud features. Scientists observed subtle bands of jet streams racing around the planet, a bright southern collar, and even massive, continent-sized storms that would appear and vanish over just a few years. One particular monster storm observed in 2014 was so bright it reflected over 30% of the sunlight hitting it, a brilliant white cap of methane ice crystals churning in the upper atmosphere. Yet these displays of weather are strangely muted compared to the constant, violent chaos on Neptune. This is the central atmospheric puzzle. Neptune, a near twin in size and composition, blazes with internal heat, which powers its supersonic winds and the famous Great Dark Spot. Uranus, as we know, has almost no internal heat to speak of. So what is driving these newly discovered storms and jet streams? The answer seems to lie with an external engine, the Sun. With its extreme tilt, Uranus presents its poles to the Sun for decades at a time. This creates an enormous and fundamentally uneven heating effect, with one hemisphere baking in perpetual sunlight while the other freezes in darkness. This solar energy, however weak at such a distance, seems to be the primary force stirring the atmosphere, creating a weather system that is deeply lopsided and seasonal on an almost unimaginable scale. Why does this solar-driven weather produce such subtle, fleeting features compared to the more robust internal heat driving Neptune's chaos? Is the planet's deep, slushy interior somehow damping the atmospheric turbulence? Or are we simply seeing a different, more refined type of meteorological drama play out on this tilted stage? The quiet blue face of Uranus is not a sign of a dead world, but of a world whose storms whisper, forcing us to listen more closely to understand its unique and enigmatic climate. This seasonal awakening reveals a deeper chemical mystery locked within the planet's distinctive blue hue. That serene, aquatic color is not from water, but from methane gas suspended high in the atmosphere. Sunlight enters the upper layers, and the methane molecules absorb the red wavelengths of light, leaving only the cool blues and greens to bounce back into space. Yet the distribution of this methane is far from uniform, and its behavior is deeply strange. As Uranus moved into its equinox in 2007, a moment of relative balance when sunlight fell equally on both hemispheres, astronomers witnessed a dramatic surge in atmospheric activity. Giant storms erupted and cloud features became more pronounced, as if the planet was stirring from its long slumber. This points to a complex seasonal pumping of methane. During the long polar summer, the sunlit pole might act like a giant chimney, driving warmer gases rich in methane upward from the deeper, hidden layers of the atmosphere. This process could concentrate the methane in certain regions, making the clouds thicker and more reflective, while leaving other areas surprisingly depleted. Why does this happen so dramatically on Uranus and not in the same way on Neptune? The answer may lie in the planet's profound cold and its lack of internal heat. With little energy from below to mix the atmosphere vertically, the system might rely almost entirely on this slow, seasonal solar heating to churn its gases. This creates a sluggish, world-sized weather machine that takes decades to complete a single cycle. The methane itself is likely being broken apart by sunlight high up, creating that photochemical haze that gives Uranus its smooth, featureless appearance from a distance. The fragments then slowly sink and recombine in the deeper, hotter layers, in a continuous, planet-wide cycle of destruction and rebirth. What complex chemical factory operates within those icy clouds, and what other exotic hydrocarbons are being cooked up in the process? The simple blue face of Uranus is a mask hiding an atmosphere of surprising and seasonal complexity. Beneath that serene blue atmosphere lies a system of captured worlds, 27 moons, each holding clues to the planet's violent past. The five largest, Miranda, Ariel, Umbriel, Teutonia, and Oberon, are a gallery of cosmic oddities, their surfaces telling conflicting stories of their birth. Teutonia and Oberon, the outermost giants, are pockmarked with ancient craters, their faces frozen in time. Ariel and Umbriel present a stark contrast, one crisscrossed with bright, fresh-looking valleys, while the other is a dark and heavily cratered relic. But it is tiny Miranda that truly defies explanation. This moon looks as though it was shattered and haphazardly reassembled by a cosmic giant. Its surface is a chaotic jigsaw puzzle of giant canyons, towering cliffs, and a bizarre feature called the coronae, a series of ridged, oval patterns that resemble a giant racetrack. Nothing else in the solar system looks quite like it. How did such a small world acquire such an intensely fractured and repaved landscape? The sheer energy required suggests a history of colossal upheaval, perhaps from a powerful gravitational tug of war with Uranus or a series of shattering impacts. This leads to the central, unresolved question about all these moons. Did they form peacefully from a disk of gas and dust that once surrounded the young Uranus, coalescing in place like a miniature solar system? Or are they mostly captured objects, wandering asteroids and Kuiper belt bodies that were snatched by the ice giant's gravity long ago? The evidence is maddeningly mixed. The regular, circular orbits of the major moons suggest an orderly formation from a disk, yet their wildly different surfaces and compositions, with some appearing icy and young and others dark and primordial, scream of separate origins and violent captures. Were these worlds born together, or did they come together by chance, creating the fractured family that circles our solar system's most tilted planet? Miranda's fractured surface looks like a world glued together from mismatched pieces. This small moon, just 290 miles across, is dominated by three colossal features known as coronae. These are vast, trapezoid-shaped regions covered in parallel grooves and ridges, resembling the tracks of a gargantuan plow. One of them, called Inverness Corona, is bordered by cliffs so high they would dwarf Mount Everest. The entire moon is a chaotic tapestry of these smooth, ridged patches brutally stitched between older, heavily cratered terrain. It gives the undeniable impression that Miranda was blown apart and then carelessly reassembled. How does a tiny, cold moon muster the energy for such extreme geology? The forces required are staggering. One leading theory proposes a history of catastrophic violence. Miranda may have been shattered multiple times by colossal impacts, its fragments swirling in orbit before gravity pulled them back together into a haphazard, lumpy aggregate. This would explain the jarring juxtaposition of terrain types, as chunks of the original crust settled next to material dredged up from the deep interior. Another idea points to internal forces. Tidal heating, generated when Miranda's orbit was more eccentric, could have once melted its icy interior. This would have fueled massive upwellings of warm, slushy ice that punched through the surface, creating the coronae as they spread and froze. The very fact that both theories remain plausible highlights the profound mystery. A shattering impact seems almost too violent for such a small body, while internal upheaval requires a heat source that is difficult to explain today. Miranda stands as a stark, fractured reminder that even the smallest worlds can hold the most violent secrets, challenging our every assumption about how planetary bodies evolve and survive. These fractured moons are not the only celestial shepherds in this tilted system. Orbiting perilously close to the planet's faint rings are tiny, hidden worlds known as the ring moons. Cordelia and Ophelia, the two inner guardians, perform a delicate gravitational dance with the most prominent of the rings, the Epsilon ring. These moons are so small and dark they were not even discovered until Voyager 2's historic flyby, and they remain incredibly difficult to study from Earth. Their surfaces are as black as charcoal, absorbing almost all the sunlight that strikes them, yet their diminutive size belies their immense influence. They orbit on either side of the epsilon ring, and their gravity acts as a cosmic fence. Cordelia, orbiting just inside the ring, tugs the particles forward, speeding them up and pushing them outward. Ophelia, on the outside, tugs backward, slowing them down and pulling them inward. This balanced, relentless herding confines the ring into a narrow, stable band, preventing the countless particles from drifting away into the void. What are these mysterious shepherds made of? Their profound darkness suggests they are coated in a layer of carbon-rich material, perhaps radiation-darkened methane ice or complex organic compounds created over billions of years. They are likely little more than porous piles of rubble, barely held together by their own weak gravity. Their existence poses a fundamental question about stability and chaos. How do these tiny moons maintain their precise orbits for eons without one being pushed into the ring or sent careening into its partner? Their gravitational ballet is a masterpiece of precision, a hidden mechanism that keeps one of the solar system's most elusive ring systems intact. What other unseen sentinels might be lurking in the darkness, silently shaping the architecture of this enigmatic world? This faint whisper of hydrogen extends far beyond the planet's blue cloud tops, forming a vast and ethereal corona. Unlike the dramatic, fiery corona of our Sun, this is a tenuous shroud of atomic hydrogen, a ghostly halo discovered by the Hubble Space Telescope. It envelops Uranus to a distance of at least 30,000 miles above the main atmosphere, a diffuse cloud glowing faintly in ultraviolet light. The very existence of this corona is a puzzle. Hydrogen is the lightest element, and on a world with such low gravity, it should easily escape into space. So why does this extended cloud persist, and what process is constantly replenishing it? The leading suspect is methane, the same gas that gives Uranus its color. High in the atmosphere, ultraviolet light from the sun relentlessly assaults methane molecules, breaking them apart. This photochemical dissection strips away the hydrogen atoms, liberating them to form the corona, while the leftover carbon likely forms heavier hydrocarbons that sink into the haze below. Yet this may not be the only source. The solar wind, a constant stream of charged particles from the sun, could also be sputtering hydrogen away from the upper atmosphere, or perhaps there is a slow, steady leak of hydrogen from the planet's deep interior itself. This hydrogen halo acts as a delicate probe into the planet's atmospheric engine. Its size and density tell a story about the balance of forces in Uranus's upper atmosphere, the intensity of the sunlight breaking molecules apart, and the rate at which the planet is slowly losing its ancient inventory of light gases. Is this corona a temporary feature, changing with the extreme seasons, or a permanent fixture of this tilted world? The answer is written in that faint, ultraviolet glow, a secret the planet has only just begun to share. Even the ghostly glow of its hydrogen corona cannot hide a more energetic secret. Uranus is emitting X-rays, a form of high-energy light that should not be so easily visible from such a cold, distant world. This discovery, made by the Chandra X-ray Observatory, added a startling new layer to the planet's mysteries. We typically observe X-rays from intensely hot sources like multimillion-degree gas in galaxy clusters or the violent surroundings of black holes. To find them streaming from a serene, icy giant was profoundly unexpected. The most straightforward explanation involves the sun. Just as sunlight scatters off our atmosphere to create a blue sky, X-rays from the sun could be scattering off atoms in Uranus's upper atmosphere, particularly from its extended hydrogen halo. Another plausible source lies in the planet's chaotic magnetic field. Charged particles from the solar wind could be funneled down toward the magnetic poles, colliding with the atmosphere and generating X-ray auroras, similar to the northern lights on Earth but in a far more energetic register. Yet here is the baffling part, the observation that keeps scientists searching for answers. the detected X-ray signal is brighter than these standard models predict. There appears to be an excess of X-rays, a surplus of high-energy light that cannot be fully accounted for by solar scattering or known auroral processes alone. This points toward a third, more enigmatic mechanism at play deep within the Uranian system. Could the planet's rings themselves be a source? Perhaps they are fluorescing, emitting X-rays as they are bombarded by charged particles. Or maybe the answer is tied to the bizarre, tumbling nature of its magnetic field. As that off-center, tilted magnetosphere churns through the solar wind, it could be creating unique and powerful electric potentials, accelerating particles to incredible speeds and generating X-rays in ways we have never witnessed before. What unseen engine, buried within its complex magnetic environment, is powering this unexpected high-energy glow? The quiet, blue world is shouting at us in a language of X-rays, and we are only just beginning to understand what it is trying to say. Even as Uranus broadcasts its high-energy secrets, a different kind of storm churns in permanent silence at its north pole. During the planet's northern summer, when that hemisphere finally tilted into decades of sunlight, astronomers discovered a giant, swirling vortex locked directly over the pole. This is not a fleeting storm, but a persistent cyclonic feature hundreds of miles across, a massive weather system that seems to be a permanent fixture of the polar summer. It was detected not by seeing cloud structures directly, but by using powerful radio telescopes to peer deep into the atmosphere, measuring the telltale signature of warm, rising air at the very center of the vortex. We see similar polar vortices on Earth, Saturn, and even Mars, giant whirlwinds that form over the winter poles, but Uranus presents a baffling contradiction. On other worlds, these vortices are typically cold core systems, fueled by the temperature difference between the dark pole and the sunlit lower latitudes. The vortex on Uranus, however, appears to be a warm core cyclone, with its center significantly warmer than the surrounding atmosphere. How does such a feature form and remain stable in an atmosphere with such a weak internal heat source and such an extreme, slow-moving seasonal cycle? The sun's energy, however faint, seems to be the key. As the pole basks in 42 years of continuous sunlight, it creates a stable, high-pressure region. The physics of a spinning sphere then takes over, funneling and concentrating this atmospheric energy into a tight, rotating storm right at the axis of rotation. Yet the stability of this vortex is what truly puzzles scientists. With so little internal heat to drive deep atmospheric circulation, and with such sluggish global winds, what prevents this swirling mass of gas from simply dissipating or wandering away from the pole? It suggests that Uranus's upper atmosphere is far more dynamically active and layered than its calm blue face implies, with hidden jet streams and temperature gradients working to cage this giant cyclone for decades at a time. Why does this particular world create such a unique and enduring polar storm? A solitary sentinel standing guard over a frozen, sunlit pole for a lifetime. That solitary polar vortex is not the only giant storm hiding on this world. Uranus occasionally reveals fleeting, shadowy blemishes known as dark spots, atmospheric features that deepen the mystery of its weather. These are not permanent fixtures like Jupiter's Great Red Spot, but rather transient, continent-sized shadows that appear and vanish over just a few years. Confirming their existence is a monumental challenge. The first convincing dark spot was not imaged until 2006 by the Hubble Space Telescope, and even then, it required the most advanced optics to pierce the planet's high-altitude haze. These spots are incredibly difficult to monitor because they are so faint, and because Uranus has such long, slow seasons. A storm that might last for 5 years is just a brief flicker in the context of an 84-year orbit, making continuous observation nearly impossible from Earth. So what exactly are these elusive dark markings? The leading theory suggests they are giant anticyclonic storms, massive high-pressure systems similar to the Great Dark Spot observed on Neptune. In such a storm, air would be sinking rather than rising. As the gas descends, it clears away the high-altitude methane haze and clouds, opening a window to a deeper, darker, and warmer layer of the atmosphere. We would see this window as a dark spot, a hole in the bright cloud deck. But this explanation immediately raises a deeper question. Why are these features so incredibly rare and short-lived on Uranus, while they seem to be more common and persistent on its sibling Neptune? The answer likely lies in the planet's profound lack of internal heat. Neptune's powerful internal energy engine drives constant, turbulent upwelling and subsidence in its atmosphere, readily forming and sustaining these giant vortex structures. Uranus, with its feeble internal warmth, lacks that powerful, steady driver. Its weather is primarily stirred by the weak but seasonally extreme sunlight. This solar energy might occasionally trigger the formation of a deep vortex, but without a strong internal heat source to keep it churning, the storm quickly loses its energy and dissipates or gets sheared apart by the planet's winds. The dark spots of Uranus are therefore like ghosts in the machine, brief glimpses of a deep atmospheric engine that sputters to life only rarely, offering us a tantalizing, frustratingly brief look into the hidden dynamics of this cold, quiet giant. This strange split personality is written across the planet's very face. Uranus possesses a puzzling atmospheric asymmetry, where one hemisphere shines distinctly brighter than the other. For decades, the southern hemisphere basked in the glow of a 42-year summer, appearing far more active and reflective than its northern counterpart. This was not just a trick of the light, but a fundamental difference in cloud cover and weather. The south developed a bright polar hood, a persistent cap of reflective methane ice crystals, while the north remained a darker, more quiescent blue. The leading explanation points directly to the planet's extreme axial tilt and its agonizingly slow orbit. The atmosphere of Uranus is incredibly deep and massive, a vast, sluggish ocean of gas that takes a very long time to heat up and cool down. This creates a staggering seasonal lag. When the sun finally moves to warm the northern hemisphere after its long winter, the deep atmosphere resists the change. It can take years, even decades, for the heat to fully penetrate and stir up the cloud-forming processes. The southern hemisphere, having just completed its multi-decade summer, is still slowly releasing its stored warmth, keeping its atmosphere more active even as it drifts into autumn. This means the planet is perpetually out of sync, with one half always responding to the season that came before. Why is this lag so much more pronounced on Uranus than on any other world? The answer may lie in the planet's profound internal cold. With no strong internal heat source to provide a steady, mixing energy from below, the Uranian atmosphere is entirely at the mercy of the sun's weak and seasonally extreme influence. It is a climate system with a massive amount of inertia, a world-sized flywheel that takes a human lifetime to change direction. This leaves scientists with a haunting question. Is this dramatic asymmetry a permanent feature of this tilted world? Or will the North eventually catch up, flipping the planet's bright and dark halves in a celestial cycle that spans centuries? These silent, frozen moons may hold the most profound secret of all. Locked away beneath their icy crusts, could worlds like Teutonia and Oberon, orbiting in the deep freeze of the outer solar system, hide vast, dark oceans of liquid water? This is not mere speculation, but a serious scientific possibility that redefines the meaning of habitability. For an ocean to exist on a world so far from the sun's warmth, it needs a powerful internal heater. The most likely source is the steady, relentless decay of radioactive elements deep within the moon's rocky core, a natural nuclear furnace that has been burning for billions of years. This heat could be enough to maintain a layer of liquid water, sandwiched between a thick, frozen surface shell and a solid core of rock. Another potential heat source comes from the subtle, gravitational tug of war with Uranus itself. If a moon's orbit is not perfectly circular, the planet's gravity would flex and stretch its interior in a process called tidal heating, generating internal friction and warmth. While the orbits of the major Uranian moons appear stable and circular today, they may have been more eccentric in the distant past, pumping enough energy into these worlds to melt their icy mantles. The implications are staggering. A subsurface ocean, especially one in contact with a rocky seafloor, becomes a potential cradle for life. The water would be shielded from the harsh radiation of space, and the chemistry at the boundary between water and rock could provide the basic ingredients and energy for simple microbial organisms. We see this principle at work on moons like Europa and Enceladus, where subsurface oceans are now considered prime targets in the search for life beyond Earth. So why have we not found such an ocean on Uranus's moons yet? The evidence is frustratingly indirect. We look for signs of a young, resurfaced terrain where liquid water might have recently seeped up through cracks and refrozen, erasing ancient craters. We search for hints of materials from the deep interior being deposited on the surface. The problem is that our data is decades old from the single flyby of Voyager 2. Without a dedicated orbiter to measure the moon's gravitational fields and analyze their surface compositions in detail, the question remains wide open. Are Teutonia and Oberon simply frozen, inert relics, or are they dynamic water worlds, hiding a secret sea in the perpetual shadow of their tilted parent planet? These silent gravitational dances create a hidden architecture around the tilted giant. Orbital resonance is not a collision, but a celestial rhythm, a gravitational symphony where moons exert a periodic tug on one another as they circle their planet. The orbits of Miranda and Ariel, two of Uranus's major moons, are locked in a perfect 1:2 resonance. For every single orbit Miranda completes, Ariel finishes exactly 2. This consistent, repeating tug creates a gravitational pulse that stretches and squeezes these worlds with clockwork regularity. This tidal flexing generates internal friction and heat, a vital force that could have thawed their icy interiors in the distant past. Think of it as repeatedly bending a paperclip. The metal grows warm from the stress. On a planetary scale, this heat can power volcanoes of slushy ice, resurface entire landscapes, and even maintain hidden subsurface oceans. The effects are written across Ariel's bright, youthful face, crisscrossed with vast networks of valleys that suggest a once warm and geologically active history, likely fueled by this very resonance. But such a delicate balance is easily broken. A passing comet, a gravitational nudge from another moon, or the slow migration of orbits over billions of years can shatter these perfect rhythms. The mystery deepens when we ask why some moons are locked in resonance while others, like the heavily cratered Umbriel, appear untouched by such forces. This suggests a turbulent past where the moons did not form in their current positions, but migrated inward or outward, temporarily catching each other in these gravitational traps before drifting apart. The rings themselves are part of this intricate dance. The narrow, confined epsilon ring is held in place by the resonant shepherding of Cordelia and Ophelia, a miniature version of the same cosmic physics. Unlocking the history of these resonances is like finding a fossilized clock. By studying which moons are locked together today and which are not, we can rewind the tape of the solar system, tracing back the gravitational shifts and chaotic encounters that sculpted this entire system into its current tilted state. This dark material is a cosmic soot that defies simple identification. It coats the ancient face of Umbriel, blankets the enigmatic ring particles, and paints the surfaces of the smaller shepherd moons in a uniform shade of black. When scientists point their spectrometers at these dark regions, they are searching for the unique chemical fingerprints that different substances leave in reflected light. The data that comes back is frustratingly vague. It shows a spectrum that is almost featureless, a flat, dark slope that absorbs light across almost all wavelengths. This lack of defining features is in itself the biggest clue. It tells us that the material is not a simple, pure compound like water ice, which would show very clear absorption bands. Instead, it must be a complex, tangled mixture, something that efficiently smothers any distinct chemical signature. The prime suspects are substances known as tholins. These are not a single compound, but a class of complex organic polymers. They are created when simple ices like methane are bombarded by ultraviolet light from the sun or by high-energy charged particles trapped in Uranus's magnetic field. This radiation breaks the simple molecules apart, and the fragments randomly reassemble into larger, tar-like macromolecules that are rich in carbon. Tholins are famously dark, often appearing reddish or black, and they are thought to be common throughout the outer solar system. Another candidate is radiation-darkened methane ice itself. Over billions of years, relentless radiation could be breaking apart the molecular structure of surface ice, leaving behind a film of pure, dark carbon, much like charring a piece of wood. So why is this still a mystery if we have plausible suspects? The problem is one of precision. Our current telescopes cannot distinguish between these different possibilities from such a great distance. A coating of tholins and a layer of radiation-processed carbon could look almost identical in our data. Each theory also comes with its own complications. If it is tholins, what was the original source of the methane ice that was processed? Was it delivered by comets, or did it outgas from the moon's interiors long ago? If it is carbon, why is the darkening so uniform across different moons with very different geological histories? The exact recipe for this cosmic paint remains locked away, a chemical shadow that has settled over an entire system, challenging us to decipher its ancient, elemental origins. This profound chemical shadow is a problem we could solve with a closer look. Yet our view of Uranus has remained frozen in time since 1986. The single greatest mystery surrounding this world might be our own reluctance to return. For nearly 4 decades, our only close-up data has come from the fleeting flyby of Voyager 2, a mission designed in the 1970s. That brief encounter was like snapping a single, grainy photograph of a complex novel, capturing one moment in a story that spans lifetimes. Since then, our most powerful telescopes have strained to fill in the gaps, but they are no substitute for being there. The scientific desire to go back is immense. A dedicated orbiter mission, armed with modern instruments, could map the entire planet in exquisite detail, monitor its weather over years, and precisely measure the gravitational tugs that would reveal the hidden structure of its interior. An atmospheric probe could plunge through the blue haze, directly sampling the chemical makeup of its clouds and determining the exact recipe of that vast, sloshing ocean of exotic ice. So why has such a mission not yet been launched? The challenges are as vast as the distance itself. The journey to Uranus takes over a decade with current propulsion technology, requiring a spacecraft robust enough to survive the long, cold cruise and then powerful enough to slow down and enter orbit, a maneuver that demands immense fuel. The financial cost is correspondingly huge, competing for priority with missions to Mars, Jupiter, and Saturn. For a long time, Uranus was simply not the top scientific target, viewed as a quiet backwater compared to the dynamic storms of Jupiter or the icy, ocean-bearing moons of Saturn. But that perception is changing. The planetary science community has now ranked a Uranus orbiter and probe as its highest priority flagship mission for the next decade. The realization has dawned that ice giants are not just oddities in our own solar system, but are likely the most common type of planet in the entire galaxy. To understand planets everywhere, we must first understand the one in our own cosmic backyard. A modern mission could finally answer the questions that have haunted us for a generation. What is the true source of its tilted magnetism? Does its deep interior hide a layer of exotic, superionic water? Are its moons frozen tombs or living worlds with hidden seas? The greatest mystery of Uranus is not on its surface, but in our own inability to reach out and touch it again, to turn the page on a story we have only just begun to read. The faint crackle of radio waves adds a hidden voice to this silent world. Uranus whispers to us not just in X-rays, but in the low-frequency radio emissions generated by its bizarre auroras. These are not the grand, shimmering curtains of light we see on Earth. The auroras of Uranus are ghostly, diffuse, and utterly chaotic, a direct result of that lopsided and tilted magnetic field. On our planet, the magnetic poles are relatively close to the rotational poles, which is why the northern and southern lights appear in predictable, circular regions around the Arctic and Antarctic. But Uranus is a different story. Its magnetic axis is tilted so dramatically that the magnetic poles are located much closer to the equator. This means that as the planet completes its sideways roll, the auroras are not neatly centered over the north and south rotational poles. Instead, they flicker to life in completely unexpected places, sometimes appearing over the equator or in the planet's midsection, tracing a convoluted path dictated by the planet's internal magnetic chaos. Why are these Uranian lights so incredibly faint and difficult to detect? The answer lies in the weakness of the engine that drives them. Auroras are created when charged particles from the solar wind are funneled by a planet's magnetic field and slam into the upper atmosphere, causing the gas to glow. At Uranus, the solar wind is already tenuous due to the vast distance from the Sun. But more importantly, the planet's off-center, tumbling magnetosphere is a highly inefficient particle accelerator. It cannot gather and focus the solar wind with the same intensity as Earth's more orderly field. The particles that do make it in have less energy, resulting in a dimmer, more dispersed atmospheric glow. This faint radio signature is therefore a crucial clue. It tells us that Uranus's magnetic field is not just oddly shaped, but also that its interaction with the space environment is uniquely sluggish. The planet's magnetosphere is a leaky, turbulent bubble that struggles to corral the solar wind, creating auroras that are as unpredictable and enigmatic as the world they illuminate. What does this weak, chaotic signal say about the stability of the magnetic field itself? And could this be a sign of a dynamo that is slowly, quietly fading away? These ghostly auroras ripple through an atmosphere of unimaginable speed and hidden violence. The winds of Uranus are a study in paradox, racing around the planet at speeds that can shatter 500 miles per hour. To grasp this velocity, picture a commercial airliner flying at its top speed, then triple it. This is the relentless, supersonic river of gas flowing over a world that is, for all intents and purposes, thermally dead. Measuring these invisible currents is a feat of astronomical ingenuity. Scientists track the movement of small, discrete cloud features in successive images, watching as they are carried along by the jet streams. They also use spectroscopy, analyzing how the light from these clouds is Doppler shifted, its wavelength stretched or compressed depending on whether the cloud is moving toward us or away from us. The data reveals a complex system of layered jets, with winds blowing both eastward and westward relative to the planet's slow interior rotation. But the real mystery is not just the speed, it is the structure. Uranus exhibits some of the most extreme vertical wind shear found on any planet. This means that wind speeds and directions can change dramatically with altitude. A cloud layer might be racing eastward at hundreds of miles per hour, while just tens of miles above or below it, the atmosphere could be moving in a completely different direction or at a vastly different speed. This creates an atmosphere that is not a single, unified river, but a stack of violently shearing sheets sliding against one another with tremendous force. So what is the engine for this atmospheric fury? The puzzle is profound. On Jupiter and Saturn, raging internal heat provides the energy to drive their epic storms and jet streams. Neptune, too, has a powerful internal heat source, but Uranus has almost none. its faint internal warmth cannot possibly account for such powerful and structured winds. The only logical power source is the Sun, despite its incredible distance. The extreme axial tilt of Uranus creates the most dramatic seasonal forcing in the solar system. For 42 years, one pole is baked in constant sunlight while the other freezes in darkness. This sets up a colossal temperature difference, not between the equator and the poles as on Earth, but between the sunlit hemisphere and the dark one. This imbalance must drive a global circulation pattern of immense power, a planet-wide effort to redistribute heat that manifests as these supersonic winds. Yet the mechanism remains hidden. How does such weak sunlight so far away manage to stir such a deep and massive atmosphere into such a frenzy? Is there some form of latent heat released when gases condense into ice crystals at certain altitudes, providing an extra burst of energy? Or does the planet's deep, slushy interior somehow interact with the overlying atmosphere in a way we do not yet understand, channeling what little energy it has into these focused Chinese letter, Chinese letter, Chinese letter, Chinese letter? The silent blue face of Uranus masks a tempest of conflicting forces, where the gentle push of distant sunlight somehow whips the sky into a hidden hurricane. This strange absence of mid-sized worlds forms a compelling puzzle in its own right. While the major moons like Titania and Oberon dominate the system, and a swarm of tiny moonlets dance among the rings, there is a conspicuous gap where the intermediate moons should be. We see this pattern clearly around Saturn, where a full spectrum of sizes exists, from the giant Titan down to countless small bodies. But around Uranus, there is a stark jump from its large spherical moons directly to a collection of much smaller, irregular lumps. This missing middle class of objects suggests a radically different history for the Uranian system. One leading theory points to a quieter, less violent past. Perhaps the primordial disk of material from which the moons formed was simply less massive than Saturn's, containing just enough building blocks to create a few large moons, but not a full range of intermediate bodies. The available material was either swept up into the giants or remained as small debris. A more dramatic explanation involves a history of colossal smash-ups. In this scenario, the system did once have a full suite of intermediate moons, but a period of extreme instability and chaotic orbital migration led to a series of catastrophic collisions. These mid-sized worlds would have shattered against one another, their fragments either being absorbed by the larger moons, escaping the system entirely, or grinding themselves down into the population of small moonlets we see today. This would leave behind only the survivors, the largest moons that withstood the bombardment, and the shattered remains of the victims. Why would this happen so decisively at Uranus and not elsewhere? The planet's extreme tilt might be the key. The same ancient impact that knocked the planet on its side could have sent violent shockwaves through the entire moon-forming disk, triggering a unique series of orbital instabilities and collisions that effectively cleared out the middle-sized class. The current moon system would then be a fossilized record of that single cataclysmic event. This missing link forces us to ask whether our own solar system's architecture is the rule or the exception, and what the silent gaps in a family of worlds can tell us about the violence of their birth. The silent hurricane of its winds hints at a climate that has rewritten itself across the eons. Uranus does not simply have weather, it possesses a deep time climate history shaped by forces operating on a scale almost beyond human comprehension. Its extreme axial tilt is the master architect of this long-term evolution, a fixed feature that orchestrates climatic dramas lasting millions of years. Current models suggest the planet's weather patterns and global circulation have not always been as we see them now. In fact, the entire atmospheric engine might have undergone radical flips and transformations throughout its 4.5 billion-year history. The primary driver of these epic shifts is the slow, gravitational waltz Uranus performs with the other giant planets, particularly Jupiter and Saturn. This dance, known as orbital precession, causes the tilt of the planet's axis to wobble very gradually over immense timescales. While the 98-degree tilt remains constant, the direction in which the pole points slowly traces a giant circle in the sky over a cycle of roughly 1.7 million years. This means that the alignment of the seasons with Uranus's orbit around the Sun changes with glacial slowness. There are periods in this multi-million-year cycle when the polar summer coincides with the planet's closest approach to the Sun, a point called perihelion. During these eras, the seasonal contrast would be at its absolute most extreme. The already intense 42 years of polar sunlight would be amplified by the increased solar radiation, potentially supercharging the atmospheric circulation and creating jet streams and storm systems even more powerful than those we infer today. Conversely, when polar summer aligns with the planet's farthest point from the Sun, the seasonal forcing would be at its weakest, possibly leading to a much calmer, more subdued global climate for millennia on end. This raises a staggering possibility. The Uranus we observe today, with its subtle storms and complex wind shear, might simply be a snapshot from a relatively moderate phase in its vast climatic cycle. What colossal, hemisphere-encompassing hurricane might rage when the orbital and seasonal rhythms perfectly align to maximize solar heating? And how would the planet's deep, cold interior and vast ocean of exotic ice respond to these multi-million-year pulses of energy? The climate of this ice giant is not a static condition, but a slow, breathing entity, its atmosphere pulsing to a rhythm set by the gravitational music of the entire solar system. That line between a planet and a star is far blurrier than you might think. Our final, and perhaps most profound, mystery asks a startling question: is Uranus a failed star? To understand this, we must first look at the cosmic engines that power the Sun and all other stars. Their immense power comes from nuclear fusion, the process of crushing atoms of hydrogen together under incredible pressure and temperature to form helium, releasing a staggering amount of energy in the process. For a ball of gas to achieve this, it needs to cross a critical threshold of mass. An object needs to be about 80 times more massive than Jupiter to ignite sustained hydrogen fusion and become a true star. But there is a curious middle ground, a celestial object known as a brown dwarf. These are substellar bodies that are too massive to be called planets, yet not massive enough to become full-fledged stars. They form like stars from a collapsing cloud of gas, and they can even briefly fuse a rare form of hydrogen called deuterium or lithium, glowing with a dim residual heat. A brown dwarf needs to be at least 13 times more massive than Jupiter to qualify. So where does that leave our ice giants? Uranus has a mass of only about 14.5 times that of Earth. To put that in perspective, Jupiter is over 300 times more massive than Earth, and even mighty Jupiter is only about 1/80th of the mass needed to become a star. Uranus is a mere 20 times less massive than Jupiter. It falls incredibly short of the mark, lacking the sheer gravitational heft to crush its core into a stellar furnace. So why does this tantalizing idea of a failed star persist? It speaks to the very nature of how these giants formed. Both ice giants and gas giants are born from the same fundamental process as stars, accreting mass from a protoplanetary disk of gas and dust. They are essentially the smaller siblings in a family of cosmic objects that range from planets to brown dwarfs to full-blown stars. Uranus represents one possible outcome of that process, a world that gathered a huge atmosphere of hydrogen and helium, but simply ran out of building material in its orbital neighborhood before it could grow any further. It is not so much a failed star as a planet that succeeded on a different, more modest scale. Its existence, along with Neptune's, helps define the lower boundary of this planetary stellar spectrum. They are a reminder that our solar system contains not just planets and a star, but a diverse collection of worlds that chart the entire journey from tiny, rocky spheres to the very edge of stellar ignition. From its impossible sideways spin to the chaotic magnetic field erupting from its slushy interior, Uranus defies every expectation. We have journeyed past its dark, dusty rings and stood in awe of Miranda's shattered landscape, a moon seemingly glued back together by a cosmic giant. We have felt the chill of its missing internal heat and pondered the violent impact that may have left it thermally dead. We have glimpsed its fleeting dark spots and listened for the faint crackle of its ghostly auroras, all while wondering about the hidden oceans that might lie beneath the ice of its largest moon. These 25 profound mysteries paint a portrait of a world built on paradox, a serene blue marble masking a turbulent and enigmatic heart. It is a powerful reminder that even in our own solar system, the greatest discoveries often lie not in the answers we find, but in the questions we are only just learning to ask. The ice giants are waiting to share their secrets, and Uranus, the tilted sentinel at the edge of our vision, holds the key. So tell us which of its countless puzzles captures your imagination the most. Is it the cataclysm that knocked it on its side, the strange ocean of hot ice churning within, or the possibility of life hiding in the dark depths of a moon like Titania? Let us know your thoughts in the comments below, and subscribe to continue exploring the deepest enigmas of space together.